Hey everyone, Geek37 back with another video, and this is part 2 in my series on the heptagonal triangle. And what I'm going to start with today is the relation of distances with the sides of the heptagonal triangle. I'm going to prove the relations there that are listed as a squared, b squared, and c squared. And I'm also going to do the one at the bottom there that's ab plus ac equals bc. Now, what's going to happen is that these identities are easy to solve using something called Ptolemy's theorem. Now, Ptolemy's theorem basically works out like this. Let's say you have a regular polygon. Every regular polygon can be wrapped in a circle just like so there. So my regular heptagon that you see on the screen labeled A, B, C, D, E, F, G can be encased in a circle. The center is right here, and you can draw a radius out to a vertex, and we could call that R. But that's not what I wanted to talk about today. What I'm going to do is I'm going to label any side length as A. If I connect across from skipping one vertex, this will be B. And if I connect skipping two vertices like so, that will be labeled C. And as you can see here in this particular triangle, ABC is my heptagonal triangle. Here is pi over 7, 4 pi over 7, which is opposite side C, and 2 pi over 7, which is opposite of side B there. So now what I want to do is I'm going to use Ptolemy's theorem to show how those relationships will work. Now, the thing about Ptolemy's theorem is if you connect diagonals across like so here, and pardon my poor drawing, as you can see here, I have A, B, C, and this is a C, and this is a C here because I'm skipping two vertices. Ptolemy's theorem, again, pardon my poor writing. Ptolemy's theorem says if we have what's called a cyclic quadrilateral inside a circle, so cyclic quadrilateral is a quadrilateral inside a circle, we can set up this way. We can take A times A, the opposite sides, plus B times C, and that will equal the product of the diagonals C times C. So we'll get A squared plus BC equals C squared. Well, if we do a little algebra, A squared, we subtract BC from both sides, we get C squared minus BC. We can get A squared equals, factor out a C, C equals C minus B, just like so there. So I'm going to go off to the side and write it. A squared equals C times C minus B. Now, the thing is, let's check out another possible quadrilateral where this will work. Let's do, change my color here. Let's say we'll do orange. Let's do here. Let's connect G to C. And of course, we got CB, AB, and AG right there. As you can see, I'm skipping two vertices on GC, so that's got a length of C. AB is down here at the bottom, so that's A. This is A, and this is A. But that's just a cyclic quadrilateral. What about the diagonals? Well, the thing is, the diagonals, we can connect across here, A to C and B to G like so here. So this length is B, and this length is B. So using the same theorem, oops, probably don't want to do that. Just erase this. So using the same setup, let's do A times A plus A times C equals B times B. So we'll get A squared plus AC equaling B squared, just like so there. So we can factor out A plus A times, or A times the quantity, A plus C equaling B squared. So that's our second one from that page. Okay, now we have a third one that we're gonna deal with. Let me erase this stuff here. So now we need to find C squared, and here's how we do it. Let's pull out another color. Let's do this dark yellow here. What I'm gonna do is connect D to F, A to F, B to D, and A to B. So these are B's. These are short diagonals. We skip one vertex here, so those are B's. This is a B as well, and this is an A. Well, where do the C's come in? Well, if we connect A to D and B to F, we're skipping two vertices, so we get the long diagonal of C's. So if we go through with Ptolemy's theorem again, A times B plus B times B equals C times C. So we'll get AB plus B squared equals C squared, just like so there. And you'll notice they both have a B here, so factor that up. B times A plus B equals C squared. So I'll write this over here in my collection. Okay. Now the thing is, there is a fourth one. These here are what I would call, they're based on what I would call isosceles trapezoids, because of the thing is, the side of any side is going to be parallel to the two diagonals that are above it, or that correspond with this. This is a truth of the regular heptagon and many other polygons as well. So that's why I would call the three of these isosceles trapezoid identities. Because as you saw in the last two examples, in this one, my sides, I had A's and I had B's, or I had C's and now I have B's that are forming the sides that are not parallel, hence why I call them the isosceles trapezoid identities. So that leaves one other type of identity that comes out of this that is non-isosceles trapezoid, but it is still what I would call a cyclic quadrilateral nonetheless. So here's what I'm going to do. I'm going to do this. I'm going to trace with a different color here. I'm going to use this blue. I'm going to trace AB, BC, and then I'm going to skip, undo. I did not expect that. And now I'll connect from C up to E, and then I go back to A like so here. That, as you can see, is also a cyclic quadrilateral, but it's not what I would call an isosceles trapezoid. Here's what happens. We have an A, we have an A, we have a B, and we have a C. Well, if we connect inside here, let's say we do with green here, I connect vertices AC and vertices EB from E to B. This is BC. So using our Ptolemy's theorem again, A times B, because A and B are opposite each other. plus A times C, those are opposite each other. And of course, what the product of the diagonals on the inside, B times C, we'll get AB plus AC equaling BC, as you can see there. Now, the interesting thing is you can actually do a lot of factoring with that. This is probably maybe one of the key identities for not just the heptagonal triangle, but the regular heptagon at large. Like I said, even though this is an exploration of the heptagonal triangle, it is also an exploration of the regular heptagon because they are both, the heptagonal triangle is within the regular heptagon, and it will go beyond that because to explore maybe just the triangle itself, you also have to explore the larger shape in order to get some of these identities down that you saw on the Wikipedia page. So as you can see here, what I can do, for example, I can factor this out. I can factor out the A and get BC, A times the quantity B plus C over BC, and divide both sides by that. This is a key identity here. And you can play around, with some of the, you can play around with the other identities there to show different ones. I might make a video on that. I haven't decided yet. But as you can see here, this is 1/2. They say that side A is equal to 1/2 the harmonic mean of the side lengths BC, which I find quite interesting. But what I really do find interesting out of this particular one, let's say if we divided this entire identity by ABC. So let me rewrite it down here. AB plus AC equals BC divided by A plus ABC, ABC, and ABC. Again, pardon me for my wretched handwriting. I can cancel out the AB's on the here. I can cancel off the AC's here, and I can cancel off the BC's here. So I get a very interesting identity, 1 over C plus 1 over B equals 1 over A. And that is a very famous identity called the optic equation. But it is one of the standard identities that is talked about in the regular heptagon, that a lot of people probably know about, but it comes from, again, just a simple use of the Ptolemy's theorem and the identity AB plus AC equaling BC, which results from Ptolemy's theorem. And you can do the algebra to get that. So you get 1 over C plus 1 over B equals 1 over A. And again, that is probably one of the most well-known identities for both the heptagonal triangle and the regular heptagon at large. And I just wanted to show you that today. I think that covers everything. So again, I hope you enjoyed this video. I enjoyed making it. This is Geek37 signing off.